In Yellowstone National Park, geologists say one of the park's famous geyser basins now has a new hot spring. Popped up in Norris Geyser Basin recently. Geologists were doing routine maintenance, checking temperatures at the basin for the first time since last fall.
Satellites scanning the Yellowstone region have picked up movements of magma deep beneath the surface, a discovery that has ignited intense scientific concern and fascination. The Yellowstone Supervolcano, an immense volcanic system stretching across Wyoming, Montana, and Idaho, has always drawn global attention because of its sheer size and potential. To detect actual shifts in magma reservoirs beneath such a formidable system raises questions about the processes underway in the Earth's crust and how such movements might reshape our understanding of this volcanic giant. Scientists, who dedicate their careers to studying volcanology, geophysics, and planetary hazards, are especially cautious when interpreting these satellite signals. The term terrified may sound dramatic, yet it reflects a mix of awe, respect, and apprehension in the face of forces that are both ancient and unpredictable. Before we start, smash the like and subscribe buttons for more updates. Yellowstone sits atop one of the largest active volcanic systems on the planet, a hotspot that has fueled colossal eruptions throughout history. 3 cataclysmic events, approximately 2.1 million, 1.3 million, and 640,000 years ago, reshaped entire landscapes and left behind vast calderas that are still visible today. Each of those eruptions dwarfed ordinary volcanic activity, producing ash layers that blanketed much of North America and altering global climates for extended periods. Modern satellite technology, with its ability to measure ground deformation, thermal anomalies, and subtle gravitational changes, gives scientists unparalleled tools to detect magma shifts that cannot be observed on the surface. The latest detections suggest that molten rock has been moving within Yellowstone's underground plumbing system, a reminder that this ancient hotspot remains dynamic and alive. The word movement here is crucial. Magma is not static. Beneath Yellowstone, a complex system of reservoirs exists, where molten and partially molten material slowly migrates through fractured rock. Satellites track even minute uplifts or depressions in the ground, and the latest data points to deformation patterns consistent with magma intrusion. To volcanologists, this is a signal that the subterranean system is reconfiguring, whether through replenishment of deeper chambers or pressure changes forcing magma into new spaces. This does not automatically indicate an imminent eruption, but it does highlight that energy is actively circulating beneath the crust. That energy, stored in enormous volumes of heated rock and pressurized gases, is what has always kept Yellowstone on the global hazard radar. When scientists admit to fear, it stems less from an expectation of immediate disaster, and more from the profound recognition of scale. The Yellowstone Supervolcano has a footprint that stretches hundreds of miles. Within this zone, hydrothermal features, geysers, hot springs, and mudpots, serve as surface indicators of the heat and activity below. They are windows into the system, but satellites now provide a deeper and more comprehensive look. Detecting magma movement means acknowledging that forces capable of reshaping continents are still at play. Scientists know that volcanic processes are not bound to human timelines, and the unpredictability of such systems is what brings unease. Even the most advanced monitoring networks cannot forecast exact outcomes, and it is this uncertainty that unsettles researchers who otherwise strive for precision. The implications of these findings ripple across multiple scientific disciplines. For geologists, the movement of magma offers insight into how hotspots evolve and sustain themselves over millions of years. For climate scientists, the recognition of Yellowstone's potential reminds them of how interconnected Earth systems are, since a major eruption could inject vast amounts of ash and aerosols into the atmosphere, altering weather patterns worldwide. For seismologists, the magma movements present an opportunity to refine their models of crustal stress and deformation. Every tremor, uplift, or thermal change adds pieces to the puzzle, helping researchers understand how a supervolcano breathes beneath the surface. Yet the grandeur of Yellowstone's subterranean activity does not translate easily into everyday comprehension. The magma detected is not a single boiling pool threatening to burst upward. Instead, it is a vast, interconnected system resembling a network of veins carrying molten material in fits and surges. Imagine immense chambers, some partially crystallized, some still molten, linked by conduits that occasionally allow pulses of magma to shift positions. Satellites capture the surface consequences of these subterranean shifts, such as bulging terrain or subtle changes in heat distribution. To scientists, these signals are both thrilling and sobering. They point to the Earth's ceaseless dynamism, where tectonic forces sculpt, reshape, and occasionally devastate. It is also important to recognize that Yellowstone is a rare natural laboratory. Few places on Earth combine such colossal volcanic potential with such accessibility for study. Researchers install seismic arrays, GPS stations, and gas sensors, while satellites orbit overhead, measuring changes invisible to the naked eye. The magma movement detected underscores how valuable this monitoring is. Without it, humanity would be blind to the deep processes unfolding beneath one of the most formidable geological systems ever discovered. This capacity to observe, to quantify, and to model does not erase the underlying reality that Yellowstone remains a place where nature's power operates on a scale difficult to fully grasp. The terror scientists express lies partly in humility. They know that human civilization, with its technology and planning, remains vulnerable to the sheer magnitude of geological events. A supervolcano like Yellowstone does not conform to human schedules or concerns. It pulses according to the rhythms of the Earth's mantle and crust, processes far older than humanity itself. To detect magma shifts through satellites is to be reminded that beneath the serene forests, meadows, and wildlife of Yellowstone National Park, titanic energies are constantly building, redistributing, and evolving. Such recognition strips away any illusion of permanence or control. Public imagination often jumps from magma detection straight to apocalyptic eruption scenarios. Scientists, however, approach it with more nuance. They understand that magma movements may occur repeatedly over decades or centuries without culminating in eruption. They can reflect replenishment events where deeper mantle plumes inject fresh molten rock into shallower reservoirs, maintaining the system's vitality, or they can signify pressure adjustments that relieve stress without catastrophic consequences. Nevertheless, the magnitude of what Yellowstone is capable of makes every signal worth scrutinizing. Even a minor eruption, localized compared to past super eruptions, could drastically alter regional landscapes and ecosystems. Thus, every new satellite reading becomes part of a high-stakes dialogue between data and interpretation. Yellowstone's role in human culture adds another layer to the scientists' unease. It is not simply a remote geological oddity, it is a national park, visited by millions each year, a symbol of natural wonder and beauty. To imagine magma shifting beneath the very ground tourists walk on transforms the landscape from idyllic wilderness to precarious frontier. Scientists carry the weight of translating such findings responsibly, avoiding sensationalism, yet acknowledging the significance. The tension between public curiosity, media framing, and scientific caution often amplifies the sense of fear. To the researchers themselves, the fear is not of certain doom, but of misinterpretation, of being unable to convey the gravity of subtle signals without sparking undue panic or conversely complacency. The story of magma beneath Yellowstone is also a story of technological triumph. Just a few decades ago, humanity lacked the ability to detect such movements with precision. Now, satellites can measure ground shifts as small as a few millimeters, mapping vast regions in extraordinary detail. These tools allow scientists to reconstruct the underground ballet of molten rock, tracking its flows and pulses across time. The recent detection represents not just a warning, but also a milestone in humanity's ability to perceive Earth's inner workings. It is a paradox of progress. The more we learn, the more acutely we feel the scale of forces beyond our control. When scientists call themselves terrified, they are acknowledging the enormity of what lies beneath Yellowstone. The terror is not born of imminent catastrophe, but of perspective. Human lifespans, even civilizations, are fleeting when compared to the geological timescales at which supervolcanoes operate. Yet satellites collapse those scales, offering real-time glimpses into movements that echo the colossal eruptions of the past. The magma shifts beneath Yellowstone are like whispers of Earth's deep time, reminders of cycles that began long before us and will continue long after. To be terrified is to respect those cycles, to know that humanity is only a small piece in a much larger, more ancient story. The consequences of these discoveries extend far beyond geology. They touch on philosophy, reminding us of our fragile place on this planet. They resonate with policymakers who must consider how to balance research, preparedness, and public safety in the face of uncertain risks. They inspire technological innovation, pushing satellites and sensors to greater precision so that the mysteries of the Earth may be better understood. Each movement of magma beneath Yellowstone, each bulge of terrain or pulse of heat becomes not just a scientific event, but a cultural moment shaping how humanity relates to the natural world. Even as satellites continue to scan and scientists continue to analyze, one truth remains clear: Yellowstone is alive. Its subterranean systems are active, complex, and unpredictable. The magma movements detected do not spell out a timetable for disaster, but they do reinforce the reality that beneath one of the most beautiful landscapes in the world lies one of the most powerful geological systems known to science. To be terrified is not to despair, but to recognize and respect the vast, untamed forces at work beneath our feet. The recent revelations from satellites orbiting high above Yellowstone have become a focal point for geologists and volcanologists worldwide. With magma movement beneath the supervolcano now confirmed, the discussion shifts toward deeper exploration of what this means for science, ecosystems, and our understanding of Earth's long-term cycles. To carry the conversation forward, one must look into the broader geological framework, the detailed science behind the monitoring technology, and the sweeping implications such activity holds for the planet. Yellowstone does not exist in isolation. It is part of a much larger mantle hotspot system that stretches deep into the Earth's interior. Unlike volcanoes formed by the collision of tectonic plates, Yellowstone Supervolcano was created by a plume of magma welling up from the mantle, burning through the crust as the North American plate slowly drifted over it. This plume is thought to extend hundreds of miles beneath the surface, a vast upwelling of heat and molten rock. The plume fuels the immense magma reservoirs lying beneath Yellowstone's caldera, and every satellite detection of magma shifts reminds scientists that this colossal engine remains very much active. Understanding the mechanics of such plumes is one of the grand scientific challenges, for it pushes the limits of what humans can truly know about Earth's interior. The satellites that revealed these movements are not ordinary imaging devices. They rely on a technology known as INSAR, Interferometric Synthetic Aperture Radar. This technique measures ground deformation by comparing radar images of the same area taken at different times. Even if the land shifts by only a centimeter, INSAR can detect it with astonishing precision. For Yellowstone, this means that bulges or subsidence caused by rising magma, pressure changes, or underground intrusions become visible in data that can be mapped across vast swaths of terrain. In addition to INSAR, satellites equipped with thermal imaging scan for subtle changes in surface heat, while gravitational satellites can pick up slight variations in mass distribution beneath the crust. All of these datasets converge to reveal that magma is on the move beneath Yellowstone, and that movement is far from trivial. For scientists, the ability to combine space-based observations with ground-based monitoring represents one of the greatest advancements of the modern age. Yellowstone is covered with a network of seismometers, GPS stations, and gas detectors. Together, they form a comprehensive surveillance system capable of sensing tremors, uplift, and chemical changes in geothermal features. When satellites pick up magma shifts, researchers can cross-check these signals with seismic swarms or unusual releases of gases like carbon dioxide and sulfur dioxide. These gases, vented through fractures and hot springs, act as fingerprints of deeper processes. Elevated CO2 levels often indicate rising magma degassing as it nears shallower depths. By correlating multiple lines of evidence, scientists can sketch a clearer picture of what is occurring miles beneath the Earth's surface. Beyond the science, the ecological stakes of Yellowstone's subterranean changes are enormous. The park is one of the most biologically diverse temperate regions in the world, home to wolves, grizzlies, bison, elk, and countless other species. The geothermal systems themselves sustain unique microbial life, extremophiles that thrive in boiling acidic pools. Any significant shift in magma movement has the potential to alter surface hydrothermal features. Geysers could become more active, dormant vents might reawaken, and entire hot spring basins could shift in character. Such changes ripple outward into ecosystems, affecting vegetation patterns, animal migrations, and water chemistry. In this sense, the magma detected beneath Yellowstone is not just a matter of geological curiosity, it is a driver of ecological transformation. From a planetary perspective, Yellowstone is a reminder of how volcanic systems influence Earth's atmosphere and climate. Past eruptions from supervolcanoes have been linked to dramatic cooling periods caused by ash and sulfur aerosols injected into the stratosphere. These particles can reflect sunlight and lower global temperatures for years. Even a medium-scale eruption at Yellowstone could loft enough material into the sky to alter growing seasons and disrupt global food supplies. Thus, every sign of magma movement is taken seriously, not because it forecasts a definitive eruption, but because it underscores the volatility of a system with planetary-scale consequences. The Earth's climate history is littered with episodes of volcanic winters, and the Yellowstone hotspot is among the few capable of producing them again. Looking backward, Yellowstone's history reveals that its immense eruptions are separated by intervals of hundreds of thousands of years. While the last one occurred 640,000 years ago, the detection of magma movement reminds us that the system is far from dormant. Even the so-called smaller eruptions and hydrothermal explosions that have occurred since are far from negligible. Lava flows poured across the Yellowstone Plateau as recently as 70,000 years ago, leaving immense rock fields still visible today. Hydrothermal blasts, where superheated water flashes into steam beneath the surface, have created craters hundreds of meters across. These smaller events, fueled by magma-driven heat, showcase the constant interplay between subsurface dynamics and surface geology. For scientists, the new magma detections are a signal that the same processes are ongoing and perhaps evolving. Another crucial element is Yellowstone's role as a comparative laboratory for other planetary bodies. Volcanologists and planetary scientists often use Earth's hotspots as analogs for features seen on Mars, Venus, and the moons of Jupiter and Saturn. By studying magma dynamics beneath Yellowstone, scientists can refine their models of how volcanic processes operate elsewhere in the solar system. Europa and Enceladus, for example, display geyser-like plumes of water driven by subsurface heat, and Io, Jupiter's volcanic moon, erupts with energy unmatched anywhere in the solar system. Yellowstone's restless magma chambers allow scientists to draw parallels, connecting Earth's inner workings to the broader cosmic story of planetary activity. The cultural and societal dimensions of Yellowstone's magma movement should not be overlooked either. Human beings, despite their technology, remain psychologically vulnerable to the idea of supervolcanoes. The very phrase evokes cataclysm, and the notion that satellites are watching magma stir beneath one of the world's most famous natural landmarks adds a layer of tension. Local communities in Wyoming, Montana, and Idaho live with the awareness that they are situated near one of the planet's most powerful geological features. While scientists strive to maintain perspective, balancing caution with reassurance, the knowledge of subterranean magma movements naturally unsettles those living in the region. For indigenous groups whose traditions and oral histories include accounts of the land's fiery past, these scientific findings echo deeply ingrained cultural narratives of power and respect for the Earth. What makes Yellowstone unique compared to other volcanic regions is the sheer scale of its underground reservoirs. Imaging studies using seismic tomography, akin to taking X-rays of the Earth, have revealed two massive magma chambers beneath the caldera. The upper chamber, closer to the surface, contains a mix of solid, partially molten, and molten rock. Beneath that lies an even larger lower chamber extending into the mantle, acting as the true engine of the hotspot. The recent satellite data indicates magma may be shifting between these layers, replenishing the upper reservoir. Such replenishment events are part of the long-term cycle of supervolcanoes, where deep mantle plumes continually feed shallower systems, keeping them alive for millions of years. Detecting these transfers through satellites is akin to catching a glimpse of the supervolcano inhaling, a reminder that it is far from inert. The human response to this knowledge often takes the form of preparedness discussions, though scientists emphasize that predicting exact outcomes is nearly impossible. Emergency planners consider scenarios ranging from localized hydrothermal blasts to larger lava flows that could reshape regional topography. The magma detected beneath Yellowstone informs these plans, serving as data points for simulation models used to explore what-if possibilities. While the general public may leap to fears of apocalypse, the scientific community channels its concern into practical steps, improving monitoring networks, refining models of magma flow, and expanding our understanding of eruption triggers. The awe and fear Yellowstone inspires also push forward technological innovation. Satellites used for magma detection are part of international collaborations involving space agencies, universities, and research institutes. As scientists analyze the latest data, they refine algorithms, enhance resolution, and even propose new satellite missions dedicated specifically to monitoring supervolcanoes. These efforts reflect an acknowledgement of Yellowstone's global importance. No other natural system on Earth is monitored with such intensity, and each new finding strengthens humanity's ability to coexist with forces that vastly outscale human society. If you like this video, please give it a like and subscribe to our channel. Also, leave your comments below and tell us, what are your thoughts on magma movement under Yellowstone? Harmless activity or looming danger? We want to hear from you. Thank you for watching and see you next time.